Welcome to our lecture video in Geotechnical Engineering with the topic Flow of Water Through Soil, or that is the Permeability and Seepage. Soils are permeable due to the existence of interconnected voids through which water can flow from points of high energy to points of low energy. So when we say permeable, it's taken from the word permeability. Okay. So permeability, or that is the ease with which water can flow through soils. Okay. Now, when we say high permeability, it means there is large soil particles, there is large space of voids, and there is better connectivity of voids. Thus, there is a higher water flow. So, take for example the larger diameters of soil here. For example, we have here soil solids compared with the much smaller diameter of soil solids. So, for higher permeability, the larger soil solids or larger particles here will provide much greater space here, or the voids. Thus, with greater spaces, there is better connectivity for voids from this point up to the next points. And if there is better connectivity of voids, then there is higher water flow. So in comparison with the smaller diameter of soil particles, so the smaller diameter here of soil solids provides smaller voids, and thus there is a much harder connectivity for the voids and much lower water flow. Okay. That's why sands have higher permeability compared to the clay. Okay. Now, how about the term impervious? Okay. So, impervious. Impervious is the term to refer to the extremely, so it's more on extreme. So the extremely low permeable soil. So that's the term for extremely low permeable soil, impervious. Okay. The study of flow of water through permeable soil media is important in soil mechanics. It is necessary for estimating the quantity of underground seepage under various hydraulic conditions, for investigating problems involving the pumping of water for underground construction, and for making stability analysis of earth dams and earth retaining structures that are subject to seepage forces. So one of the major physical parameters of a soil that controls the rate of seepage through it is the hydraulic conductivity, otherwise known as the coefficient of permeability. And it is given with the symbol K. Okay, so look at this figure here. So this is the setup used by Sir Darcy. So we will be using the Darcy's law. Darcy's law governs the flow of water through soils. Sir Darcy proposed that the average flow velocity through soils is proportional to the gradient of the total head. Now for the full video of the explanation of the Darcy's law, a link to a YouTube video is provided in our class. And feel free to visit that also in our playlist. I will put that video in there also for better and more illustrative explanation. Okay, so here are the formulas to remember, which we can derive from the work of Sir Darcy. Okay, so first formula we have here is the velocity of flow. It is also known as the discharge velocity or the average velocity. So take note of these three names for this symbol V. Okay, so in different problems, these three names can be used. So if sometimes the name used is velocity of flow, sometimes they will use discharge velocity, and sometimes it is average velocity. So watch out for these terms. Okay? So V, or velocity of flow, is equal to the K. K is the hydraulic conductivity or the coefficient of permeability. And then we have here I. I here is the hydraulic gradient, where I is equal to the head over the L. So from the figure, look at this figure here. So where do we get the H? H is the difference in head. Okay. From this point here, of the region of higher energy, of course the potential energy there, and the lower energy or region of lower potential energy. So the difference in the head is H. Okay? So the difference of this water level here is the H. Then the L here is the distance traveled of the water from the point of from this point to the point where we took the level of the water. So this is the distance traveled by the water, because the water is being entered here at this portion here. The water enters here and then flows horizontally through the soil and goes out to this exit, goes out to this tube here. And then the measurement was taken from this tube to this other tube, and that's the length of the travel of the water in this soil. Okay? So it is important to know this setup, because the tricky part in the problem will be on how the soil is being set up. Okay. You must always remember L is not always horizontal. L is the distance traveled by the water from the point of two different observation points. Okay? So the observation point here is this portion here and this tube here, where we took the difference for the head, H. Okay? So that's the setup. It is important because even if we incline the soil sample here, we can still get the correct answer. We are not just memorizing formulas, but we are also understanding the setup of different experiments. So this is experiment of Sir Darcy, and we are trying to understand how he came up with these formulas. Or we need to see the designation of different parameters used here. Okay, so that's for the hydraulic gradient. Okay, next we have so we're done with the velocity of flow. Velocity of flow is also equal to discharge over the area. Now the question here is, what is this area here? This area A here is actually the cross-sectional area of the soil. The cross-sectional area of the soil. And it is always perpendicular with the flowing water. So again, let's go back to the setup. So where can we get the value of A, or the area? So if the water is flowing from this portion here and then goes through the soil and goes out here, the flow of water, if we are looking, this is our eyes and its side view. Okay, if we are looking here, we can see here either a circular cross-section or a square cross-section. And we need to make sure that it is perpendicular to the flow of water. So if it is a circular cross-section, then we get the area of a circle. Okay? So we must always remember that. So that's for V. Velocity of flow, we sometimes call this VQ. Next, the seepage velocity, V sub N. The V sub N is equal to the velocity of flow, this one here, over the N, or the porosity. Okay? So if the given is the void ratio, so we need to solve first the porosity before we are able to get the value for seepage velocity. Okay. So that's for the Darcy's formula. So we also have here the flow of water. Flow of water is Q is equal to, of course, this is Q is equal to VA, right? QVA. And using hydraulic conductivity, we will obtain QKIA. QKIA being Q is equal to hydraulic conductivity times the hydraulic gradient times the cross-sectional area. Okay? Let's go to the two laboratory tests. So we have here two standard laboratory tests used to determine the hydraulic conductivity of soil. We have the constant head test and the falling head test. Let's differentiate these two. So first we have the constant head test. A typical arrangement of the constant head permeability test is shown in the figure below. Okay, so it's still hidden. So here is the figure. Let's put it there. Okay. So in this type of laboratory setup, the water supply at the inlet is adjusted in such a way that the difference of the head between the inlet, so this is the inlet, and the outlet remains constant during the test period. So if you notice here, the difference in head H from the inlet here up to this point, obviously, no matter how long is the water open here, the value of H remains constant. So that's the reason why it's called constant head test, because the head here is constant. Okay, so the inlet and the outlet remains constant during the test period. After a constant flow rate is established, water is collected in a graduated flask for a known duration. The constant head test is used to determine the coefficient of permeability of coarse-grained soils. Okay, so that's for constant head test. Okay, so CC, constant head test, coarse-grained soil. So CC. Let's go to the other test. Let's go to the formula first of constant head test. So here is the formula for a constant head test. for its value of K, or hydraulic conductivity, or what's the other name for hydraulic conductivity? That is coefficient of permeability. So it's here. So for the value of K, we have there V, that is the volume collected, volume of water collected in time T. Then we have there L, the length of soil sample. Of course, that is the distance that the water have traveled. So obviously we have here a vertical flow of water. And then we have T, duration of water collection. A is the cross-sectional area of the soil, and H is the constant head. So thus we have the formula for hydraulic conductivity K is equal to VL over TAH. Now, in order for us to remember it, this formula, we assign the V here as volume. Okay, so VO as the volume length over time area H, or we call that volta. So K is equal to volta. Again, to remember the velocity a while ago, we have V key. To remember the formula for Q, we have Q kia. And then to remember the K here is we have volta. So in such way, we can easily remember the formulas. Okay, let's go to the second test. We have the falling head test. A typical arrangement of the falling head permeability test is shown in the figure below. Okay. So we have here the figure. So water from the standpipe, so this is the standpipe, flows through the soil. So this is the soil. The initial head difference H1 at the time T is equal to 0 is recorded. For the initial time, so this is the standpipe, so this is the initial water level. It will flow through the soil. It will flow through the soil, then out into this tube, and then goes out there. So initially we have H1 here at time is equal to 0. Okay? So at time 1 is equal to 0. And then water is allowed to flow through the soil specimen such that the final head difference at time T is equal to T2, or T sub 2 is H2. Or that is, if we have here the faucet, for example, the flow of water, okay, so we will fill this up to this point, and then we will switch off the faucet, and then we will allow this level of water to go down up to this point here, wherein the difference between this point up to this point is H2. H2 will be at time 2. Okay? So that's why it's called falling head test, because the level of water goes from here up to here. Okay? Falling head because H1 obviously is greater than H2. And time 2 is greater than time 1. Okay? The falling head test is used for fine-grained soils. So it's used for fine-grained soils. Why? Because the flow of water through this soil is too slow to get reasonable measurement from the constant head test. So FF, falling head test, fine-grained soils. So the reason why we are using falling head test is because, as mentioned a while ago, the smaller the diameter of soil solids, the slower the water moves from one point to, or from one void to another. So that's why the water is allowed to stay here at this smaller pipe. It will be allowed to go down at a certain level, allowing it to flow through the much smaller voids for the fine-grained soils. So that's for the falling head test. Formula for hydraulic conductivity for falling head test is K is equal to LA. So the L here is the length of the soil. The length of the soil wherein the water traveled, the distance the water traveled. The smaller a is the cross-sectional area of the standpipe. We have there H1, that is the head at time 1. And then we have H2, that is the head at time 2. And then we have the A, the bigger A, which is the cross-sectional area of the soil. Okay. So the formula thus is equal to K is equal to la ta, so this is time, then A, la ta ln H1 H2. Okay. So T2 minus T1, because T2 will always be greater than T1. And then we have here H1 over H2, having H1 as greater than H2. Or should be H1 is greater than H2. Okay? So I hope that helps in remembering these formulas. K is equal to ln H1 over H2. Okay, let's go to the flow through permeable layers. Permeable layers are layers wherein water can flow. Impermeable layers are water wherein the water are soils. Sorry. Okay, so the permeable layer is the part of the soil, a soil wherein the water can flow. Impermeable layer is the soil wherein the water cannot flow. The soil layer wherein water cannot flow, or it can flow lesser. Okay? Impervious, low permeability. Now the formula for the hydraulic gradient for this one, for the this setup. So remember, the hydraulic gradient I is equal to the difference of head over the L, or the distance traveled by the water through the soil. Now, what happens if the soil is inclined? So we are taking a point from this well up to this point here. And the difference of the water level, or the head here, is equal to H. So we have here the H. So we can see we have H here, we have H here. How about the L? Okay, so let's name the L here as the horizontal L, the horizontal distance from point here up to this point, the higher point up to the lower point. To get the value for the distance traveled, for distance traveled of the water, so we will take here a triangle. Okay. Oops. So let's just assume this is straight. Right triangle there. So this is the L. Okay. Now what we are taking here, or what we are solving here, is the distance traveled of the water through the soil here. Let's name that L prime. So this is the L prime here. L prime. Okay. And we have here an angle alpha. So angle alpha. To get the value of L prime, or the distance traveled of the water from this point up to that point there, so we have there cosine of alpha is equal to L over L prime. So L prime is equal to L over cosine alpha. Substitute the value of L prime to this formula here. We get the value I is equal to H over L cosine alpha, or that is equal to I is equal to H cosine alpha or over L. So that's for the hydraulic gradient of this setup here. If the given is the horizontal distance of the higher point here, point A to point B. Okay? So that's how it is derived. The next setup is this one. What if the horizontal distance is not given, rather the only given will be the difference of the head. The difference of the, of course it will be consistent. So the difference of the head. So how did I is equal to sine alpha get there? So again, let's draw a triangle. Okay, so this is the triangle. The angle here is alpha. Then this is right triangle. And taking, actually this is taken from here. Okay. So right triangle there. Okay. So from a specific point here and up to there, okay, consistently the angle is the same, alpha. So we can say here that the difference of head between 2 points, at any 2 points on this surface, we have there H. And what we're looking for is this one here, the L prime, so that we can satisfy the equation I is equal to dH over dL prime, or the distance traveled by the water in the soil. So to get L prime there, we have, and the given is H, so we will use sine alpha is equal to H over L prime. L prime is equal to H over sine alpha. Okay. Now if we substitute L prime here, we now have H all over H sine alpha. So we have here H sine alpha all over H, cancel H. Now you have I is equal to sine alpha. So that's why we have here the formula I is equal to sine alpha if the given is H. Okay, so those are the formulas. Let's apply them on some of the sample problems before we proceed to more formulas here of different setup for permeability. Okay, let's apply what we have learned so far. Okay. So we have here example number 1. Okay. So this one here will be about formula. For normally consolidated clay soil, the following values are given. So it's only one soil sample. Void ratio is 1 at void ratio 1.1. Hydraulic conductivity is, so at void ratio 1.1, the hydraulic conductivity is 0.302 times 10 to the power of -7. At void ratio 0.9, the hydraulic conductivity is 0.12 times 10 raised to negative 7. It says here, the hydraulic conductivity for normally consolidated clay is given by the following equation, where E is the void ratio, C sub 3, and N are constants to be determined experimentally. Determine the value of N, determine the value of C sub 3, and determine the hydraulic conductivity of the clay at a void ratio of 0.75. So we're looking for K here. Right, so let's solve this. So what can we observe from this scenario? One soil sample, a normally consolidated clay. From our previous lessons, what can we learn from void ratio? So you can have different void ratio of one soil sample because of its different condition, right? So we have the natural state, the dense state, the loose state. So at different states, so the void ratio becomes different also. So it means that these are variables, so they change. They change depending on the value for the void ratio. Of course, N also changes here. So using this, given K, given E, missing the 2, so we are looking for C3 and N. So we need to use two equations, two unknowns. And to do that, we need something that we can equate the two equations so that we can solve it more easily. Again, from what we are analyzing here is this void ratio and hydraulic conductivity, they change, as well as N, the porosity N, because the value of N depends on the value of the void ratio. The question here is the C. C is a constant. Okay? So it is a constant. It is definitely fixed. Therefore, we will equate the two equation using C sub 3. Okay? Since C sub 3 is the same, okay, so let's just equate here. C sub 3 sub 1 is equal to C sub 3 sub 2. And then the formula, so if we are using here C sub 3, C sub 3 is equal to K times 1 plus 3 all over E raised to N. Therefore, we have here K sub 1, 1 plus E sub 1, or why did I put there 3? Should be E. There. Okay, all over E sub 1 raised to N is equal to is equal to K sub 2, 1 plus E sub 2 all over E sub 2 raised to N. And actually it's N sub 1 and then or N sub 2. Oh, so it says they're constants. So the problem already mentioned that they are constant. Okay, so because if we will not treat this as constant, it means we actually have three unknowns, N1 and N2. So if we analyze it carefully, C2 and N, C sub 3 and N are constant to be determined experimentally. So these two are already constant. So if that's the case, then really there is 2 equation and 2 unknown. Okay. So if that is the setup, so we have here A sub 1 over K sub 2 equals, we have there E sub 1 over E sub 2 raised to n, and then we have here 1 plus E sub 2 all over 1 plus E sub 1. Okay, and then input the values for K1 and K sub 2, A sub 1, and then A sub 2. So we have there 0.302 times 10 raised to negative 7 all over 0.12 times 10 raised to negative 7 is equal to 1.1 all over 0.9 raised to n, which is the missing value. And then we have here 1 plus 0.9 all over 1 plus 1.1. Okay? So, using our calculators, so we have here 0.302 times 10 raised to negative 7 over 0.12 times 10 raised to negative 7. So we have here this is already 2.5167 divided by this. So we're making some shortcuts. Okay. So that is 1 plus 0.9 over 1 plus 1.1. 2.78. So we have there 2.7815. Yeah, 1579 is equal to what is 1.1 divided by 0.9. That is 1.222242 raised to n. Okay, so we can direct that in the calculator, but if you don't have any capability in your calculator to do that, so we can just use log. So this is n log of 1.222 is equal to log of 2.781579. So n is equal to 2.7579 Let's wait for the value. So that is 5.1, 5.098 or 5.1. Okay, so n is equal to 5.1. Or if you want the so 0.9. Okay, so that's for letter A. Now letter B, let's determine the value of C sub 3. Let's just get one formula here. So K sub 1. K sub 1 is equal to C3 times E sub n, E sub 1 raised to n, then 1 plus E sub 1. Okay, K1 is 0.302 times 10 raised to negative 7 equals C3. Then we have here 1.1 raised to 5.098 all over 1 plus 1.1. So C3 is equal to, so we have here 0.302 times 10 raised to negative 7 times 2.1. So we have there 0. So I got in my calculator 3.901 times 10 raised to negative 8. And since it is a constant, you don't have any unit. So we have there C3. Now let's have C. Estimate the hydraulic conductivity of the clay at a void ratio of 0.75. That becomes E sub 3, 0.75, looking for K sub 3, question mark. Okay, so let's get again the formula. K sub 3, since we have the value for C3 already, C sub 3, we have 3.901 times 10 raised to negative 8 times 0.75 raised to 5.098 all over 1 plus 0.75. So what is K3? K sub 3. So we have 3.901 times 10 raised to negative 8 times 0.75 raised to 5.098 over 1.75. That is 5.14. 5.143 times 10 raised to negative 9, and the unit is centimeter per second because the unit here is centimeter per second, so we are using also centimeter per second. So that's for number 1. So screenshot it first. Okay, so let's go to example number 2. For a constant head laboratory permeability test, okay, take note, says there constant head. So CC, constant head for coarse grained soil. So for a constant head laboratory permeability test on fine sand, the following values are given. We have the length of specimen L is equal to 10 inches. Diameter of specimen 2.5 inches. Head difference H is equal to 22 inches. Water collected in 2 minutes is equal to 0.044 cubic inch. And the void ratio of the specimen is 0.34. Letter A, determine the conductivity K of the soil in inches per minute. B, determine the discharge velocity through the soil in inches per minute. And then C, determine the seepage velocity in inches per minute. Okay, let's go back again to the discussion of velocities. We have 2 types of velocity. We have the V and the V sub S. So take note, it did not use the term velocity of flow. The term used was discharge velocity. So B here, what we are looking for here is V. And for letter C, the V here is V sub S. Okay? Now again, what's the formula for hydraulic conductivity for constant head test? So here is the constant head test. Now here is the formula, volta. Okay? Let's use volta here. So K is equal to volta, volume, length of the travel of the water through soil, time, cross-sectional area, head difference. Of course, the head difference here is constant. Okay, let's see, we have given for length. Length of specimen is given. The h, or the diameter of the specimen, so we can solve for area. And we have here so what's the question? Hydraulic conductivity K. So we have here the volume. So we have the volume. Where is the volume here? Oh, yeah. 0.044 in cubic inches. Then we have the value H as 22 and the time is 2 minutes. Okay, so let's solve this. So input all the values. So we have here volume of 0.044 cubic inches. Are they all in harmony? Okay, so they're all inches. Okay, so this 0.044, the length of the specimen is 10 inches all over D. We have the time of 2 minutes. So the answer we're looking for is in inches per minute. So there's no need to convert. 2 minutes. Then the area. Pi over 4 times the diameter of the specimen, 2.5 inches squared. And the H is 22 inch. Okay, so we have the final answer here will be in inches per minute. So of course this is inches squared, this is inches cube, and then this is inch. So cancel inches per minute. Okay, so we're good to go for the unit. Let's just solve this. So 0.044 times 10 all over 2 times pi over 4 times 2.5 squared times 22. So the answer here is 2 points. So K is equal to 2.037 times 10 raised to negative 3, and then we have their inches per minute, or inch per minute. So that's for hydraulic conductivity. For letter A. What's the next question? Determine the discharge velocity. Again, what's the formula for discharge velocity? Vicky. So we're going to use Vicky. So B. Key. So 2.037 times 10 raised to negative 3. The unit is inch per minute. And take note, the hydraulic gradient does not have a unit because the unit will be cancelled. Again, what's hydraulic conductivity? For hydraulic gradient, sorry. So for hydraulic gradient, I is equal to the difference in head all over the length of the travel of the water through soil. Or in our example, that is the length of the specimen. Okay. So length of the specimen here. So H is given as 22 And then the distance traveled or the length of the specimen is 10 inches. 22/10. So V is now equal to 2.037 times 10 raised to negative 3 times 22/10. 4.48. We have here 4.48 times 10 raised to the power of negative 3 inch per minute. That's for B. Let's go to C. The question for C is the seepage velocity. For seepage velocity, we have V sub S is equal to V over N. So Vs V over N. Now, the question here is, what's the value of N? We need the value of N. And we can get that because there's a void ratio here. So, to solve for the value of N, we have there N is equal to E over 1 plus E. Our E is 0.34 all over 1 plus 0.34. So N now is equal to 0.34 over 1.34. 0.2537. 0.2537. Therefore, V sub S is equal to 4.48 times 10 raised to negative 3 all over 0.2537 is equal to 765 times 10 raised to the power of 2, negative 2. And that is in inch per minute. V sub S, seepage velocity. Okay, so that's for number 2. So screenshot first. Okay, let's go to number 3. A soil sample 10 centimeter in diameter is placed in a tube 10 meter long. So there's a soil sample. So this soil sample here, the diameter is 10 centimeter. So we can imagine the cross-sectional area here is circle. And the tube here is 1 meter long. And it is inclined. A constant water supply or a constant supply of water is allowed to flow into one end of the soil at A and the outflow at B and is collected by a beaker as shown. So if there is the word constant supply of water, so this is a constant head test. Okay? The average amount of water collected is 1 cubic centimeter for every 10 seconds. 1 cubic centimeter in every 10 seconds. So we have that as Q, the flow rate, Q. Okay, so let's write that down here. So it says there, we have 1 cc in every 10 seconds. So if that is 1 cc, so we have there 0.1 cc per second. So that's the flow rate. The tube is inclined as shown. Letter A, determine the average velocity of flow through the soil in centimeter per second. Average velocity. And that is here. So V key. So that is V. Determine the seepage velocity through the void spaces, so V sub S. And then determine the coefficient of permeability of the soil. Coefficient of permeability or hydraulic conductivity, that is K. Okay, so let's solve first for V. Given here, V, remember that aside from V key, we can also have V is equal to Q over A. So we can already solve this because Q is already given. So letter A, we have there V is equal to Q over A, 0.1 cc per second. This is pi over 4. The diameter is given. Diameter given 10 centimeter in diameter. Okay. So 10 centimeter in diameter, 10 square. So V now is equal to 0.1. So 1.27273 centimeter per second. So 1.273 times 10 raised to the power of negative 3 centimeter per second. So that's for letter A. Next, we need to look for V sub S. That is seepage velocity, and that is equal to V over N. So we need to solve first for N, and you can see in the figure given is the void ratio. So N is equal to E over 1 plus E. N is equal to 0.6 all over 1 plus 0.6. So N is equal to 0.6 over 1.6, 0.375. So V sub S now is equal to 1.273 times 10 raised to negative 3 all over 0.375. So V sub S is now equal to 3.395 times 10 raised to negative 3 centimeter per second. Okay, now let's go to letter C. We're looking for coefficient of permeability K. So coefficient of permeability K, we can use once again for the constant volta. Can we use this? Time collected 10 seconds. Volume collected is 1 cc. But actually, we can already get the value by using QKIA. So you can use volta, Ku is equal to volta. You can also use QKIA. So having here the value of Q given, area, of course, let's find the hydraulic gradient, I. So I is equal to the difference in the head. So obviously, the first one here is here. Now, the tricky part is up to this point here. If you let the water flow, okay, if you let the water flow from this point here up to this point here, and the water is being caught by a beaker over here. Where does the water go? The water goes inside the beaker. If you allow it to flow, what happens? It will fill this beaker up to the point here. Okay, so the beaker will be filled here. Now, where is the level of water now? It's 0.8 as shown in the figure. So the difference of H will be taken from this point here up to here. So to get the value of H, we need to add 1 and 1 here. 1 plus 1 is 2 minus 0.8. And that is the value for H. Okay, for I, that is equal to 2 minus 0.8 all over the distance traveled by the water, not horizontally, but inclined. So the water is flowing inclined, and it is 1 meter. So here we have I is equal to 1.2. So Q, a while ago, it's 0.1. K times 1.2, then pi over 4 times 10 centimeter diameter squared. So we can now get the value of K is equal to over 1.2 times pi squared. And the value is 1.061 times 10 raised to negative 3, and the unit is centimeter per second. Okay? So that's for number 3. Screenshot first. Okay, let's go to the example number 4. A sand layer having the cross-section area as shown. So we have here the sand layer, the one it's talking about is here at the portion here. Okay. A sand layer having the cross-section area as shown has been determined to exist for a 350 meter length of a levee. Now, where is 350 meter length here? 350 meter length is perpendicular to the paper that we're looking at, because this levee here, if we draw that, in 3D, of course, it will be like this, that. So it is continuous. Therefore, we can get the 3D of this soil layer below the levee as, so if we draw that, so this is the soil layer under the levee. Okay? If we take that as such, okay. So in this levee here, we have the 110 meter here, and then this is the 350 meter. The flow of water is from this portion here, and then goes out here into the ditch. So in our drawing here, so the flow of water is from this portion here, then goes out here. So that the flow of water is parallel to 110 meter, and then it is perpendicular to 350 meter. meter. Okay. So that's the setup. Okay. The coefficient of permeability of the sand layer is given. It is 3.5 meter per day. Determine the flow of water into the ditch in liter per minute. So what we're looking for here is the value of Q, or the flow rate. We're looking for the flow rate, and we know that for flow rate, it's easier if we use the Q-Kia. So Q-Kia. So given the K, a while ago it was given as 3.5 meter per day. 3.5 meter per day. Okay, so let's just solve for the value of hydraulic gradient I. So from this figure, for the hydraulic gradient, we have here the difference of the two elevations. So this is the H. And the length will be the distance traveled by the flow of water. When we say the distance traveled by the flow of water, it is the direction parallel to the flow of water, and that is the 110 meter. Okay? So if I solve for the hydraulic gradient, that would equal to 140 minus 120, the elevation, all over the 110 meter. And that is equal to, so what is 20 divided by? That is 20 over 110, or 2 over 11. So let's just use that here. Okay, so let's just put here 20 over 110. Okay, so for Q now, that is equal to, what are we looking for? It's in liter per minute. Q in liter, Q is question mark, in liter per minute. So we need to convert. If K is 3.5 meter per day, so we need to convert that into, so in 1 day, we have how many minutes? So 60 times, so we have 360. So because in 1 day we have 24 hours, and in 1 hour, okay, so for the conversion we need to show it more clearly. Let's put this here. Okay, meter per day, and then in 1 day we have there 24 hours, and then in 1 hour we have 60 minutes. Okay, and that is equal to 3.5 over 24 times 60. So we have there 7 over 2880. So cancel hours, cancel, that is meter per minute. So 7 over 2880 meter per minute. And then for I, that is unitless, 20 over 110. For the area we have there pi over 4. No, it's not pi over 4. You got used to the circle. So the area is area is perpendicular to the flow of water. So what we're using here is 350 meter. And the thickness of the sand layer is 1.5 meter. Okay, so it is 350 meter times 1.5 meter. That is equal to 7 times 20 times 350 times 1.5 divided by 2880 times 110. So it's 0.232 cubic meter per minute, and multiply that with 1 liter in it should be 1,000 liter in every 1 cubic meter. So Q now is equal to 232 liter per minute. So that's the value of Q for number 4. Okay, so screenshot first. Okay, so now let's go to number 5. A falling head permeability test was run on a soil sample 9.6 centimeter in diameter. So the soil sample here is 9.6 centimeter in diameter, and it is 10 centimeter long. The head at the start of the test was 90 centimeter. So the head at the start is 90. So at okay, so it's, let's say there each there. So at the start of the test, remember this is falling head test, so we have 2 values for time and 2 values for head. So at time 1 is equal to 0, H1 is equal to 90 centimeter. The coefficient of permeability of the soil, okay, so the coefficient of permeability of the soil was found to be 5 times 10 raised to negative 6 centimeter per second. The diameter of the standpipe, so this one here, is 1 centimeter. Determine the flow at the start of the test in cubic centimeter per hour. Flow in cubic centimeter per hour, it's looking for Q. Then B, determine how much head was lost during the first 30 minutes. What we know here is it's talking about head, but the tricky part here is it's looking for how much head was lost. Okay, the question here is that H2 or is it the difference of H1 and H2? Okay, we'll find that later. Letter C, determine the flow after 30 minutes in cubic centimeter per hour. And that is, again, Q. Okay, let's start with, okay, so we took all data. Okay. So let's start with letter A. The flow at it's looking for the flow at the start of the test. Looking for the flow at the start of the test, let's try QKIA. Since K is given, and we have the value of H at the start, which is 90. We have L, and we have the area, so it's QKIA. So this is 5 times 10 raised to negative 6. So are the units consistent? Centimeter, centimeter, centimeter. Okay, so they're all consistent. Then for I, we have their H, 90 centimeter over the 10 centimeter L, and then the area circular because it's diameter. Pi over 4, 9.6 squared. So Q is equal to, so what we're looking for here is in per hour. It's in per centimeter per second here. So just emphasize. Let's put here centimeter per second. Right? So Q is equal to, so 5 times 10 raised to negative 6 times 90 over 10 times 5 over 4 times 9.6 squared. So 3.257 times 10 raised to negative 3. This is in centimeter per second. Multiply that with this is second. So how many seconds in 1 hour? So in 1 hour, in 1 hour we have 60 minutes, and then in 1 minute we have 60 seconds. So Q is equal to 3.257 times 10 raised to negative 3 times 60 times 60. So that is 360. So 11.725 cubic centimeter per hour. So that's for letter A. Let's go to letter B. What we're looking for is how much head was lost during the first 30 minutes. Okay, let's find the value of H2 at time 2, because the time 2 here is 30 minutes. Time 2 is 30 minutes. And H2 is question mark. So what can we use here? Remember, falling head test is volta. No, let's constant head test. Falling head test is lata. The time, that is time 2 minus time 1. The area, cross-sectional area, lata ln H, the greater one, H1 over H2. So that's the formula. Now we have the value for K, the L, the A also here, we also have here. So yeah, we can get the value for H2. So K here is, okay. So H, 30 minutes. So let's convert this into seconds. So here we have 30 minutes times 60. So we have here 1,800 seconds. So yeah, I need to confirm. Yeah, 1,800 seconds. So K is 5. That is 5 times 10 raised to negative 6 equals L. L is 10. The area of the standpipe is, so 1 centimeter diameter. So we have pi over 4, 1 squared all over. This is 1,800 minus 0. Then the area is pi over 4 times, how much again is the area? 9.6 diameter. 9.6 centimeter in diameter. Ln of H1, that is 90, then H2. Okay, so if we solve for H2, see, so it's 82.84. centimeter. Now, the question here is, determine how much head was lost during the first 30 minutes. It's not asking determine the head after 30 minutes. If it is determine the head after 30 minutes, then that is H2, H sub 2. But it's asking determine how much head was lost during the first 30 minutes. So it means it's looking for H is equal to H2 minus H1. H2 is 80, it's H1. It's H1 minus H2. That is 90 minus 82.84. So H is equal to 7.16 centimeter. So that's for H. That's for B. Now let's go to C. Determine the flow after 30 minutes in cubic centimeter per hour. That is Q. So letter C, use Q Kia. So what's going to be different here? Again, let's use the value for K. Okay, the one we use here is 5 times 10 raised to negative 6. And then we have there the I. The value of I after 30 minutes is 82.84 all over 10. And then pi over 4, 9.6 squared. So that is equal to, so we have 2.998 cubic centimeter per second. So if we convert that into cubic centimeter per hour, that is 10.79 cubic centimeter per hour. So that's for letter C. Okay, so that's number 5. Screenshot first. Let's proceed to number 6. A permeable soil is underlain. So a permeable soil is underlain by an impervious layer. So watch out for the words underlain. So meaning there is something below it, and that is an impervious layer. Okay? So a permeable soil is underlain by an impervious layer as shown in the figure. For the permeable layer here, K is equal to 0.0048 centimeter per second. H here is 3 meters, and alpha here, the inclination, angle of inclination is 5 degrees. Letter A, calculate the hydraulic gradient I. B, calculate for the flow of water per meter width in cubic meter per hour. So it says there per meter width, so that is small q. Then letter C, calculate the total amount of water percolated per day per meter width in cubic meter. So total amount of water, that is volume. Okay? So let's solve for letter A. So this setup is same with what we have discussed earlier. Again, we have there I is equal to H over the distance traveled by the soil. So it is inclined. Let's put there L prime. So that is H. So this is H over, we have there L prime here. So the angle alpha, so perpendicular. This is L prime and this is L. Okay, so meaning if this is H, okay, so let's that. So if this is H, we are going to use sine. So we have there sine of alpha. Oh no, it's H over sine alpha. Cancel out, so this is sine alpha. Okay, so I is equal to sine alpha. I is equal to sine of 5 degrees. So I is equal to 0.08716. Now let's go to letter B. So what's being asked for letter B is the small q, the flow of water per meter width in cubic meter per hour. So we have there small q, Kia. The difference is that in the cross-sectional area, the length is not given. So what we're looking for here is the value of H. What I mean by the L is not given. So if this is 3D, again, if we draw this as a 3D, so if this is the inclined soil, okay. So we have here the value for H. Okay, so it's given. The value of H is given, but the question here is what is the value for this one here? It's not given, because when we are looking for the value of area, it is the perpendicular to the flow of water. Alright, so how do we do that? Given H as 3 meters, so H is equal to 3 meters. This is inclined. So if this is H of 3 meters, is inclined. And what we're looking for is the perpendicular to the flow of water. It's always perpendicular area. So this one here is the perpendicular area. So how can we represent that? So we're looking for, if this is the flow of water, we're looking for this one here. But what's given is here. Okay. So it's not that super inclined. Okay, so there. We're looking for if the water is flowing like that. Okay, so it touches the area in a perpendicular manner. So perpendicular manner. Okay, and what's given here is a 3 meter width or height of the soil. So obviously, we have the angle alpha here at this portion. So we have angle alpha here. Now the question is, where is the perpendicularity? Where is the, if we draw the triangle, of course this is the alpha. And where is H and where is the L? So since this is longer, Okay, so this is H here, will be treated as the longer leg of the triangle. So this becomes the hypotenuse, and then the other leg will be here. Okay, and we have triangle. Perpendicular triangle, treating H as the hypotenuse. So this is H is equal to 3 meter. This is what we're looking for, the L. Okay, so we're looking for the L. So to get the area should be here at this portion here. So L times 1 because it's in per meter width. So L times 1 is the area. So area is equal to L times 1. Now value for alpha is equal to 5 degrees. So for L, we have there cosine alpha or cosine 5 is equal to L over 3. So we now have here 3 cosine of 5 times 1. So that is area A. So yeah. Okay, so I think we got the point. So what is 3 cosine of 5? So this is 2.988. Okay, or 2.99. So let's say 2.99, and the unit is meter squared. So what are we going to get again? Cubic meter. Okay. And then the given K is 0.0048 centimeter per second. So K is 0.0048 centimeter per second. So this is multiplied with 100 because we have there 1 meter, or multiplied, divided by 100. So K is equal to so that is 4.8 times 10 raised to negative 5 meter per second. Oh wait, we're looking for per hour. Okay, so per second, so per hour, so one minute is 60 seconds. 1 hour is 60 minutes. Okay. So we have there 0.0048 over 100 times 60 times 60. So we have K is 1.33 times 10 raised to negative 3. Cancel out minute, cancel out seconds, cancel centimeter, that is in meter per hour. Okay, and then we have I already, so for complete, K is 1.33 times 10 raised to negative 3 meter per hour. I is 0.08716. Then A is 2.99 meters squared. So Q is now equal to 1.33 times 10 negative 3, 0.08716 times 2.99. So the answer is 3. So cubic meter per hour. Okay, let's check this. So 1 meter per centimeter. So, okay. Now I get it. And I was wondering why it is so small. So this should be 60 seconds in 1 minute. And then we have here 60 minute in 1 hour. So I was wondering why it's so small. Okay. So the value for K is incorrect. So 0.0048 times 60 times 60 over 100. So that is 0.1728 meter per hour. 0.1728 times 0.08716 times 2.99. So 0.045 cubic meter per hour. So that is flow. Now, letter C, we're looking for the total amount of water percolated per day given Q. So we know that Q is equal to volume over time. And how many hours? Oh no, total amount percolated per day. So it's asking for per day. So volume is equal to QT. Q is 0.045 cubic meter per hour per day. So in 1 day. In 1 day, that is 24 hours. So that is equal to 0.045 times 24, 1.08 cubic meter. So that's for the volume. Right? So that's for number 6. Now let's go to the last one. We have number 7. Okay? Water flows through the permeable layer as shown. Given H is equal to 3.5 feet. So 3.5 feet. H here is 4.6 feet. L is 120 feet. Alpha is 14 degrees. And K is equal to 0.0016 feet per second. Then consider 1 feet width perpendicular to the figure. So per feet width. Calculate the hydraulic gradient I. Calculate the flow of water Q, small q, per feet width in cubic feet or cubic foot per hour. Calculate the total amount of water percolated per day per feet width in cubic feet. So volume. So looking for, again, the volume. So first is the hydraulic gradient I. So again, the setup a while ago, because it is inclined, given the L. So the drawing here is a triangle, right triangle, alpha 14 degrees, 120 feet. So what we're looking for is L prime. So I is equal to H over L prime. H, so H is 4.6 feet. L prime is, this becomes cosine of 14 equals L over 120, no, that is 120 over L prime. So L prime is equal to 120 over cosine of 14 degrees. So we have here L prime is 120 over cosine of 14. I is equal to 4.6 over 120 over cosine 14. So the answer here is in percent. So it says there in percent. Times 100. 3.72%. So that is the value for I. Let's go to B, the flow. Calculate the flow. So again, we have Q Kia, small q, Kia. And again, what we did a while ago is that what we need is the perpendicular to the flow of water. So we have here, and then we have the given. Oops. So this is the permeable layer. The given here is H, and then this is the right triangle. We will treat the given H here as the hypotenuse. So the triangle formed here alpha 14 degrees, and we are looking for L prime. Hypotenuse H is equal to 3.5 feet. So if we are looking for L prime will be equal to, so L prime is equal to sine. So this is sine 14. Where are we using sine again? Cosine. So we're looking for, we're using cosine. 14 equals L prime 3.5. So L prime is equal to, so L prime over 3.5. Oh yeah, that's correct. So L prime is equal to 3.5 cosine 14. So going back here, so in what unit again are we going to use? In hour, per hour. So let's convert first K. So K is equal to 0.0016 feet per second. Convert that in hour. So we have there 60 seconds, 1 minute, 60 minutes in 1 hour. So K is equal to 0.0016 times 60 times 60. So 5.76 feet per hour. So Q is now equal to K of 5.76 feet per hour, I of 0.0372. So we're not using percent. Then area is L, that is 3.5 cosine 14 times width 1. So Q is now equal to 5.76 times 0.0372 times 3.5 cosine 14 times 1. So 7277 cubic feet per hour. So that is for Q. Now last, we have letter C. We're looking for the volume. So volume is equal to QT. So that's what we had a while ago. So Q is 0.7277 times per day. So 24 hours. Cubic feet per hour. Per day, we have 24 hours. So volume is now equal to 0.7277 times 24, 17.46 cubic feet. So that's for number 7. So screenshot first. Okay, so that's all for this first part of the video. We will continue on our next video.